Yeah, in the last three lectures, we covered the basics of probability, right? We started with basic, uniform probability distribution over discrete sets, right? So we were counting things, and we saw there are like many subcases of counting. You need to be careful whether things are ordered, unordered, distinguishable, not distinguishable. Yeah, and then we looked at, yeah. So what else did we look at? So we looked at infinite sample spaces and the problems associated with it. And then thirdly, we also looked at conditional probability. Yeah. So what happens when you are given some partial information, and what are conditional probability distribution and the relations between them. Okay. So today's lecture is going to be just doing a problem solving on these three topics. Okay. So that we are very clear. And later, either on Monday or Saturday, I will make an announcement in the evening. We will have a deep quiz, okay, on these topics. Okay, so we there will again be a office hours tomorrow evening. So you will have had enough time to look at the material, absorb all these three lectures. So after that, it's good to have a deep quiz, which we'll have either on Saturday or Monday. Okay. Yeah. So yeah, let's try to solve some problem.
So deep quiz will also be in MCQ format.
Sorry.
So deep quiz will also be in MCQ format, or we'll have to give detailed solution.
Let me just send you a message in the evening. So we are making plans on how to do it. Yeah. So
okay.
Yeah, most likely it will be just like your light quiz. You will need to submit in the website. Yeah, so we'll let you know about the details by today evening. Okay. Okay, let's focus on some problem solving now. Okay, so these are from problems from the reading materials that I gave you only. Okay, so these are some very common problems that appear in probability, which illustrates some important ideas. This is called the birthday paradox. Okay, so suppose you have k people. Okay, so we are around more than 100 people in this class. Yeah. What is the probability that two people have the same birthday? Yeah, how do you compute this? So yeah, where is the probability? What is the sample space? Yeah. How do you approach this problem?
Hello?
Yes.
Sir, actually we can use the complement of this. That is, we can subtract the probability of none of the people are having
No. Wait a minute. Yeah, we haven't got there. What is the sample space?
All the days of the year.
All the days. That's the sample space.
Yes, sir.
365 power k will be the sample space.
360 per k is the size of the sample space. Is that right?
Yeah.
And so what is the sample space? Give me some some set. So what is the sample space omega? Give me some set, so that we want to be extremely clear about what we are doing. So what is the sample space here?
So every element of the sample space will contain k dates, and there will be 365 to the power k such elements.
Is that ordered, unordered?
Unordered. Or it doesn't matter actually.
Doesn't matter. Yeah. So yeah, in some way I agree with you that it doesn't matter. But let's say we are in this class. Okay, there are 100 people in this class. Yeah, I can sort your names in alphabetic order. There is the first person. Yeah, there is one person who's is coming first in the alphabetic order. His birthday could be any of the 365 possible things, right? So let his birthday be A1. Yeah. There's a second guy in the alphabetic order. So his birth, his or her birthday is A2, and similarly there are K people, and each of this AI belongs to 1 to 365. This is the sample space. Is that clear? Yeah, it's a sequence, ordered sequence. Remember, it's a tuple. That is, it's ordered. If I write A1, AK, this it's a set. Order doesn't matter. But here it's ordered. That's why it is that round brackets, not the curly brackets. Curly brackets means order doesn't matter. Inside a set, order doesn't matter. Okay. And what is the size of omega? As many of you has already pointed out, it is 365 to the power k. Yeah. And what is the problem? What is the probability that at least two have the same birthday? So how do you compute that? So I think Rishabh initially said that, okay, instead of computing that, it is better to complete the complement. So how do you do that? Any ideas?
So for first person, the size of sample space should be 365. But for second person, the size will reduce by 1. That's why it should be 364. And then it goes on till k people. At the last person, the sample space size should be 365 minus k. I think it should be.
So you are saying this is not correct.
No, this is correct. This is correct. But for calculating the probability in the case when no one is having the same birthday. Like,
okay, so let me just write that probability that no one has the same birthday.
Yeah.
So the complement of this is the probability that we want.
Yeah.
Great. Okay.
So the first person will be having the birthday.
Let's go slowly. So
Yes.
what's the denominator?
365.
Totally.
Yeah. And numerator 1.
Denominator is only 365.
For first person. Now it will multiply 365 into 364 into 363 till k people.
So this denominator I have to just write 365, is it?
No, sir. 365 into 364.
I had to write here 364.
Yeah, 364.
That I should write the denominator or the numerator?
So denominator.
Does everybody agree?
No, sir.
Denominator will be 365 to power k.
365 to the power.
So denominator is the total number of possibilities.
Yes.
This is 365 raised to k. Yeah. And yeah, what Mahak was saying, possibly the numerator. Possibly you were confused about that. So the first person could go into any of the 365 days.
365.
The second person cannot go into the first person's same date, because otherwise we have a problem. Yeah. 364 up to okay. Up to how many should I go on?
365 minus k minus 1.
Just confused. Yes, sir.
365 minus
K minus 1.
Minus k plus 1.
Minus k minus 1 minus k plus 1. Which one?
Minus k plus 1 if you don't give the bracket. And if
Yeah.
you keep k minus 1 in bracket, then k minus 1.
Okay, is that clear to everyone?
Yes.
So fine. So yeah, it is some number. Yeah. Yeah. So yeah. So yeah, how does this number look like? This looks like
So 365 pk.
this is 365 pk. Okay. Yeah, sure. I mean, we are just interested in this number. That is fine. Okay. And the probability of yeah, probability of this event, let's call this event A, is 1 minus of this number. Okay, is that fine? Okay, so can you think of this as a bolts and bins problem? So we earlier discussed the bolts and bins problem. Can you think of this as a bolts and bins problem?
Yes, sir. There are 365 bins in this case, and no two balls can go to the same bin.
Is that clear? So there are bolts which are the people. Are the bolts distinguishable or indistinguishable?
So distinguishable.
Distinguishable because each person has a different name. Each person has a different face. Yeah, it's distinguishable. And the bins are the days, right? The birth date has to be something. And is the bins distinguishable? Again, it's distinguishable because the dates are different. I know the 1st of January from the 5th of August. Yeah, and yeah, so many problems actually reduces to the balls and bins problem. Okay, that's why that problem I mentioned in the first place. Okay, so any problem you take, you can think of it as the balls and bins problem, where some things are distinguishable, some things are not. Okay, so that is good. Yeah, what about this? Okay, so you have a committee of, 5 people to be selected from 6 men and 9 women. Yeah. So how many ways can you do it? So what is the sample space?
So 15C5.
15C5. Yeah. So does everybody agree?
Yes, sir. Yes, sir.
So
Yes.
we don't care really their names or yeah, we only care about their gender, but we don't really care about their names, because the second part of the problem is not asking for anything about the names or anything. It's just saying there are 3 men and 2 women. Yeah. So in this case, the sample space, you can think of it as, so you need to select, so yeah, what is the sample space? That's a good question now.
So 15C5.
15C5, okay, that you are saying it's the size of the sample space.
So sample space will be the different combinations of men and women that will comprise to make total 5 members in a group.
Okay, so yeah, yeah,
Like
so
we can have 1 man and 5 women, and there will be similar other combinations as well.
okay.
Oh. So sample size would be the different set of 5 elements.
It will be the different set of 5 elements. Okay. So there is a set of men. So let's say there is a set of men, M. So M is this a set 1 to 6. Yeah. And then there is a set of women. It's a set of 1 to 9. Yeah. And yeah. So we need to, so let's also kind of slightly differentiate it, which is M1 up to M6 and W1 up to W9. Yeah. And we want a subset of 5. So basically the sample space is the set of S, which is a subset of M union W. You agree? There is a set of men, there is a set of women, and we are looking at, subsets of M union W. Yeah, and the size of the sample spaces. We also want the size of S to be equal to 5. So this is your sample space. So the way it's possible is 6 plus 9, which is 15. So you are choosing from a universe of 15, some 5 people. Is that clear? Yeah. So yeah, I mean, intuitively it's very clear, 15C5. But how does that come? You have to be very careful. Yeah. Now, yeah, what is the probability that the committee consists of 3 men and 2 women? Yeah. So it's again a numerator by denominator. And what is the denominator? It's the size of the sample space. So it is 15C5. And what is the numerator? Yeah, how many possibilities are valid for this particular event? Yeah.
So
Only one.
9C2.
Only one.
Yeah, 6C3 and 9C2.
So should I add them or multiply them?
Multiply.
Multiply.
So there's this set of 6 things. So in the numerator is basically I'm looking at subsets S such that the number of S intersection M is actually 3 and S intersection W is actually exactly equal to 2. Yeah. So the way to create such a set is I will just pick from the 6 men I will just pick 3 and from the 9 women I will just pick 2. Yeah, is this clear? So it's just plain simple calculation. Yeah? So okay, so possibly many of you already know this, but yeah, if you write in terms of set, things become very clear if in case you are confused. Okay. Okay, so assuming everybody is clear with this, let's go to the next question. So yeah, so just to be clear, okay. So suppose you have a set 1 to n. Yeah, so there are some n people. Yeah. You can sample a random element from the set. Yeah, I can choose a random person from the set. Yeah. I can choose it multiple times. First I choose somebody, second, then I choose somebody, then I choose somebody, then I choose somebody. So you are making a sequence of choices. So R1 is chosen from A. Then R2 is chosen from A. So these are chosen randomly. Yeah. So when you make a sequence of choices from a set, okay, there are 4 possibilities. Yeah. So the first possibility is the choices ordered or not. So what that means is, okay, you are choosing the first person to be chosen and then the second person and then the third person. Okay, so who was the first person to be chosen, who was the second person to be chosen, who was the third person to be chosen. Yeah, and you are doing with replacement. That means after you choose the first person, in R2 also, R1 is also a possible choice. I'm not excluding R1. I'm not removing R1 from the set A when I choose again. Yeah. So if I do an ordered choice with replacement, how many possibilities are there? So let's say I make 3 choices. Yeah, how many possibilities are there for R1?
N cube.
Yeah, so this is there are n possibilities for R1. Again, n possibilities for R2 because R1 is not removed from the set A. And another n possibilities for R3. Let's say you have to make k things, then you n raised to k. Yeah. So this is k, so n raised to k. What about without replacement? What do you mean by without replacement? I chose R1, but then I removed R1 from the set.
NP3.
So how do you get that NP3? I mean, that's a formula.
So, first we'll be having n choices and then n minus 1 choices as we are not replacing it, and then we have n minus 2 choices.
So up
n
to
minus
n
k
minus
in
k
general plus 1.
Yeah, so yeah, this is, you can directly arrive at this formula without any NP3 thing. Okay, I prefer to understand this directly at this, because it's very, look at the formula, it's clear what you are counting. Okay, but if you use that NP3 formula, it also works out as this number. Okay, now what if it is unordered? That is, this choice of R1, R2, R3 was done behind closed doors, and then you are told, okay, there is this group of people which was selected. Yeah. So yeah, how many possibilities are there?
NC3.
NC3. How do you get that?
Just that like for the first, we have to select three we have to select three elements from a set of n elements, and the order doesn't matter.
Yeah.
So like for the first choice, we have in, like, similarly what we had with ordered, it's just we divide by 3 factorial, because here the order wouldn't matter.
So
Like in, yeah.
I mean, is there a problem there? Because so you are saying it is, let's say for 3 people, it is just n into n into n divided by 3 factorial. Is that what you're saying?
No. I am saying that it would be NPK upon 3 factorial, like NP3 upon 3 factorial.
So it is for without replacement, and you are writing for with replacement.
So I'm writing for without replacement. So
Sir, unordered, then like NC3 into NC2 n minus 1 C2 into n minus 2 C.
How are you getting all this? I'm not completely confused.
Sir, actually,
unordered. So in from n number of, like, if you consider like, and there are n balls, that is unordered. So we have to select it first. So that's why for selection we use C. So
okay,
so actually we can arrange k things in k factorial ways. Now here arrangement does not matter because the things are unordered. So in both the formulas, we will just divide by k factorial.
So you are saying the answer is n raised to k divided by k factorial. Is that you are raising?
So this is for with replacement.
This is with replacement.
Yes, sir.
This is with replacement.
So n to the power k
the
by
answer
k
for with
factorial
replacement is n raised to k
by k factorial.
But with ordered with sorry, so there is a confusion here. Yeah. So without replacement, so if it was ordered, it was this number. Yeah. So
yes,
it was ordered, it was this number. Now the problem is this choice was done behind closed doors, and then you are given a group of people. We are not told who was the first choice or second choice or third choice, but all the choices are different. Yeah. So I could actually permute them in any order in k factorial possible ways, and all of them corresponding to the same choice when it is unordered. So this is the number.
Sir, it will be the number of partitions. Maybe.
No. Is this explanation clear?
Yes, sir.
Yes, sir.
Because, I first choose these people according to this, but here I know who was the first person, who was the second person, and everything. But all of them are distinct. Yeah. But so if I did the choice behind closed doors and reveal the choice to you, you don't know in which order I have chosen. But there are only k factorial different orders. So yeah, so I will be repeating the same thing k factorial different times. So I just divide by k factorial to avoid that different situations. Yeah. Okay, now what is this thing with replacement? How many?
So similarly, as we have done in case of ordered with replacement, we can just divide by k factorial to remove the arrangements.
Okay, but does everybody agrees with this? Is there a problem with this?
But there may be repetitions.
So suppose I chose the 3 persons to be the same. All my 3 choices were the same first person. I mean, then there is only one way I could have come up with this, no? But you are dividing by 3 for that. How can that happen?
So now we have to divide with individual counts of those that are repeated.
Okay, so let's say we want to look at 3 people. So how do you get the number? So we agree that this is not the correct answer. Is that clear to everyone that this is not the correct answer?
Yes, sir.
So what is the correct answer?
Sir, can you repeat your explanation once?
Yeah.
So can you repeat your explanation once?
So what are we doing? We are doing this with replacement. Okay, I selected this with replacement. Let's say n cube. Yeah, there are n cube possibilities, and then you are. I am opening the door and revealing the set of people to you, right? And you don't know whom I chose first, whom I chose second, or whom I chose third. Okay, so you will say, okay, you could have done it only 3 factorial possible ways. So I will just divide by 3 factorial. But the problem is it's not always 3 factorial. I might have chosen the same person 3 times. Then it doesn't matter who, in which order I chose. Is that clear?
Yes, sir.
Yeah. The ordered tuple 1, 1, 1. There is only one way of writing the ordered tuple 1, 1, 1. Yeah. But if I take the ordered tuple 1, 2, 3, I can arrange this in 3 factorial different ways. Yeah. Here we didn't have a problem because it was without replacement. So all the people were distinct. So yeah, I mean, there were k factorial choices which lead to the same choice when I reveal the people to you. But here you need to be a bit more careful. So what is the right answer here? Let's say for k equal to 2. What is the right answer here? I think for k equal to 2, we already did it. Nobody want to give a try? Okay.
Sir, for k equal to 2, we can do like this. K is equal to, like if there are n people, so n1 plus n2 plus n3, n3 up to nn. So it will be like stars or bars type of problem maybe. I'm not sure.
No. I think you're complicating too much. You remember the first problem we start with dice? Yeah. So suppose let's assume that the 2 numbers that I chose behind closed doors was different. Yeah. Then there was n into n minus 1 possibilities. Yeah. For each of them, if that was the case, I could have revealed there were 2 choices in my view, which will be the same as 1 for you. So then I will divide by 2. But there is also n cases where I chose the same person twice. And each of them is a different case for you also, related to you. So is that the correct answer for k equal to 2?
Yes, sir.
Yeah. So what happens for k equal to 3?
Sir, we have to take 3 cases when all the 3 are different, when 2 are same, and when all the 3 are same.
Okay, let's just try to do that. So all the 3 are different, everybody kind of agrees. Yeah, this everybody agrees. Okay, now, and the last case also everybody agrees. Yeah. So behind the closed doors, I chose 3 different people. That is this. Behind the closed doors, I chose the three of my choices were the same person. So then there's only this possibility. And what happens here? Suppose I chose 3 people, but there are only 2 distinct people in that 3.
So we have to divide by 2 factorial then.
Yes.
Have to divide by 2 factorial. Okay, what do we have to divide by 2 factorial?
N into n minus 1 divided by 2 factorial.
N into n minus 1 divided by 2 factorial. Does everybody agree?
No. Sir, n square divided by 2 factorial.
N squared divided by 2 factorial. Okay, does everybody agree?
Yes, sir.
So I am making, I am seeing the entire thing. I am doing this behind closed doors. I am actually doing, yeah. So what is the possibility? Let's say I chose A1, A2 and A3. Yeah. I am looking at the case when 2 of these are the same. Yeah. So there are 3 cases actually. Within this particular case, there are actually 3 cases. Yeah. So the case 1 is A1 equal to A2, not equal to A3. Yeah. Then there is A1 equal to A3, not equal to A2, and A1, A3 equal to A2, not equal to A1. My first choice could be equal to the second choice and not equal to the third choice. I mean, I could get 2 different people in these 3 possible ways, no? You agree?
Yes, sir.
Yes, sir.
Yeah. And yeah, so now how many choices I have for this?
Excuse me, sir.
Yes.
Sir, but this way aren't we ordering them?
Yeah. In my view, I am ordering them. When I give it to you, I will do the division. So okay. I agree. There should be a 2 factorial division in the end. Yeah, that 2 factorial division need to be there. I agree.
Okay.
But when I am doing behind closed doors, for me it is like a ordered choice. Yeah, with replacement. Yeah. Okay, sir. And we are only looking at cases where I am only choosing 2 distinct people. And then when I reveal it to you, relate it to you, it is it is just a set, unordered. Yeah. So first time, so remember in the dice case also, we first assumed that everything was ordered and calculated the probability, from which we derived the probability when it was unordered. Yeah, because it's always very easy to calculate in the ordered setting.
Right, sir.
So A1 equal to A2. So the number of possible choices for, once I fix A1, A2 is also fixed. So this is n squared. So there is 3n squared. Yeah, so all of this is n squared, n squared, n squared. Sorry, n into n minus 1. I'm sorry. Yeah, so there are 3 n into n minus 1. And then I can divide by 2 factorial. I could have done it either way. Yeah, so is that clear? Okay.
Sir?
Yes.
Sir, why we multiply by 3? As they are unordered, so it can be anything. A1 can be A3 also, and A3 can be A2 also.
So let's say I am choosing these people behind closed doors. Yeah. For me, I am seeing the entire thing. I am choosing the first person and then choosing the second person and then choosing the third person. And then I am revealing these three people to you without telling you the order in which I chose them. For me, there are three cases. The first two choices of mine was the same and the second choice was different. Or the second two choices were the same and the first was different. Or the first and last was the same and the second was different. Yeah. So there are all these three possibilities for me. And in each of these three possibilities, when I reveal it to you, I could have chosen in two different ways and still given you the same set.
Yes, yes.
Yeah. So, yeah. So, yeah, I mean, this number is always a bit complicated. Okay. It's not easy to arrive at. For k equal to 3, it was easy to work out. You can try to work out what happens when k equal to 4 and higher things. Okay. It will be a very interesting exercise.
Sir, can you please explain with a small example?
This is not a small example.
Okay.
So I was choosing three people.
With numerical values.
So this was a numerical example. Sorry.
Sir, there are total n people.
So you just want to substitute n equal to 5 or something. Is that what you're saying?
Yes, sir.
So yeah, I mean, you can substitute n equal to 5 and then you will get 5 into 5 minus 1.
Yeah, okay, sir.
Yeah, when this is the simplest example I can think of.
Okay, sir.
Yeah, even simpler example we did in the first lecture itself. Actually, the 2 dice. Yeah. Okay. So.
Sir, I didn't understand why we are dividing by 2 factorial.
Okay, so let's say, I mean, I am choosing this 3 people, right, behind closed doors. Yeah. So let's say I got, I mean, the first person, I got first person, and then I got the fourth person. Yeah. When I reveal the people to you, I am not telling you the order. I am only giving you the set 1, 4. Or I mean the set 1, 1, 4.
But sir, but there are 3 factorial by 2 factorial number of ways of arranging 1, 1, 4, right?
3 factorial by
2 factorial.
I mean, so if you have, I mean, A1 different things, sorry, if you have a sequence of length n, yeah, where there are n1 different things of which are of same type, n2 different things of which are of the same type, yeah, how many ways are there of arranging?
N factorial by n1 factorial, again divide by n2 factorial.
Yeah, so and so on. So there are some, maybe some, there is nt. Yeah, it will be number of ways of arranging. So n1 of them are similar, n2 of them are similar, nt of them are similar. So it is n factorial divided by n1 factorial up to nt factorial. So there are 2 different things here. So I mean, yeah, 2 of type 1, 1 of type 4. Yeah, the number of ways of arranging is 3 factorial divided by 2 factorial into 1 factorial.
Yes, correct.
So yeah, and actually that's how this 3 comes.
Excuse me, sir.
Yeah.
Sir, I have a doubt. Sir, but if we consider this way, then we are considering these 3 arrangements as different outcomes. Like 1, 1, 4 is different and
1 4 1 will be different. These 3 factorial divided by 2 factorial, these 3 permutations are these 3 basically. 1 1 4
You're
1 4
saying as
1
I said.
4 1 1. But this way we are considering them as
Just a
ordered.
second. Yeah, just a second. Yeah, maybe I got confused a bit. So you're saying you don't need to consider these 3 cases at all.
So basically I think we can approach this problem in this way. So
I see.
when
So you don't need this 3, yeah?
no, we don't need.
Yes, sir. Yes, sir.
Yes, sir.
But
Yeah,
we need
so
a 2 here. We need a 2 here, sir.
Yes, sir.
just a second. Oh, no, there is something going on which is yeah. So I think I got confused here a bit. Yeah. So yeah, I mean I could choose according to each of these 3 choices, and it will remain the same actually. So it doesn't matter which I am choosing from. So yeah, the right way to look at this is there are only n into n minus 1 divided by 2 factorial choices. Yes.
But sir, we have to consider those 2 cases. Then there will be either 2 1 1 4 or 1 1 and 2 4s.
Sir,
Yeah. Sorry.
we can say like this that we are choosing two person from n person, and there are two possibilities. Like first person comes two times or second person comes two times. So NC2 into 2 factorial. Oh, sorry, into 2. Because there are
Exactly.
two possibilities.
Exactly.
Yeah.
Can I repeat, sir? If you want.
So yeah. So I mean. The thing is, when I just a second, in the number of possibilities, just a second. So yeah, I mean there is some intersection. When I reveal it to you, there is some intersection between these 2 cases. So okay. So these are already covered in this.
Excuse me, sir.
Yes.
Hello, sir. I think that 3 should come because which two A1 A2 in which two we are choosing the same 3C2 into n minus n by 2 factorial. That's why the 3 has to become.
So let me get back to this part later. Okay. So right now I'm a bit confused. So I will give a proper explanation for this later. Okay. Okay, let's move on to another problem. I mean, right now it will be like if I talk more, I'll again get you more confused. But let's move on to another problem. Okay. Yeah. So suppose you roll a dice 10 times. You are rolling the dice 10 times. Yeah. Now, what is the probability that you see 1 3 times, 2 4 times, and 3 2 times? So what is the sample space? Yeah, so you are throwing it 10 times. Okay. Yeah. So yeah, suppose I mean I was noting down things one after the other. So there are is A1 to A10 can be belonging to the set 1 to 6.
1 to 6.
Yeah. So the size of the sample space is A1 is 6 possibilities. It is 6 raised to 10. Yeah. And yeah, what is the probability that this happens? So the probability of seeing 1 3 times, 2 4 times, and 3 2 times. How do you do this? Yeah, so the denominator is 6 raised to 10. So in how many ways can you do this? So there are 10 throws. Yeah.
Sir, can I try?
Yes, yes.
Sir, first we are considering 1, so 10p3. 10c3 into 3 factorial, 10p3. Then 3
why
is
that
gone.
10p3?
Sir, we can select 1, means we can select any of the 3 dices which will show 1. That we can do in 10c3 OS.
Okay.
And then they can be arranged in any of the arrangements, so into 3 factorial.
Does everybody agree with that?
As they are similar, there is no concept of arrangement in that.
Yeah.
So you only need 10c3.
Sir?
So sir, all the dice are similar here?
No.
No, all the
times you are
numbers
seeing
on the dice.
All the numbers in the dice are similar.
That I am not saying. I am saying about the dice. That 3 dice can be any of the 3 dices out of 10.
No. But those 3 dice are showing the number 1. No. You cannot distinguish between those 1.
Oh, okay, sir.
So there's no need for arranging between those ones.
Okay, sir. Then 10c3 into 7c4 into 3c2.
7c4.
Yeah, because only 7 is remaining now, and from 7 we need 4.
Some 3 places are already fixed. Yeah, we already said these are 3s. Then remaining 7 things. 7c.
7c4. For 4 2s. 7c4.
And
into
then
3c2. Into 3c2.
So then, so we also fixed some 4 places. Let's say 4 places. So now 3 plus 4, it is 7. So there is only remaining 3. So 3 how many times? 2 times.
2 times. So 3c2.
We are done.
Into 6.
Why is there a 6?
So one roll is left.
And
one
what
dice
are the
is left.
possibilities
So
for that?
one dice can show 6 different possibilities.
Can it show any of the 6?
No, it will be multiplied by 3 instead of 6 because we cannot have 1 and 2 and 3 now.
Yes.
So the only possibility is 4, 5, 6.
Did everybody get that?
Yes, sir. But in that case, we won't be having denominator as 6 by 10. It should be 6 power 9. Yeah, I got it, sir. And one more thing, I have a doubt in this. Like we can choose 2 first, like 10c4, and then we can choose out of 7, we can choose once.
Yeah. So you are saying instead of doing this, you will do 10c.
Yeah, there is a chance, like 10c4 and then 7.
And 7c.
6, sir. 6c3.
Sorry, 6. Yeah, 6. And then what will you do? Again, there is 7.
3c2.
3c2 into 3.
Yeah.
So all this would lead to 10 factorial divided by 4 factorial into 3 factorial into 2 factorial. So like it wouldn't matter what the order is, like how we choose it.
So it's magic. So you proved something.
No, but technically it's not magic because a denominator has 10 minus 4 factorial, which is 6 factorial, and the next term has 6 factorial in its numerator, so it gets cancelled. That is what I'm saying.
Yeah. In some way, it is not magic, but suddenly, if you look at these 2 formulas, you will wonder, oh, why are these the same? Like, yeah. But if you had the story behind, it's obvious why it is the same. Yeah.
So I didn't get why are you multiplying 3 in the numerator?
Okay. Why is this 3?
Yeah.
So we have chosen this. We have filled up 9 places after this.
Yeah.
Okay, so we have filled up some 9 places. So this guy is yet to be chosen. Yeah, we have fixed all the values of the 9 places. Yeah, but there is this guy sitting there. There are 6 possibilities for that.
Okay.
Yeah, but can I substitute any of the 6 possibilities? Because if I substitute a 1, then 1 will be there 4 times. So I cannot substitute any of these 3 possibilities. I can only substitute the remaining possibilities. So there are only 3 possibilities for this.
So, but when we are actually doing 10C3, 7C4, 3C2, that one person which is left, like the order is coming inherently into it. So why are we multiplying 3 with it? Because when we are if we have to select 5 people, and if we are selecting if we are selecting 3 people, if we are selecting I'm not able to put it actually.
So actually, she want to say that why we have to consider that last role. Why we'll consider that if you have already taken in like 10C3, 7C4, and 3C2.
But
so I'm saying that in this thing 10C4 into 7C 10C3 into 7C4 into 3C2, the order is inherently coming. That one place which you are taking extra, which you are taking for 3, that we do not need to consider it.
No, I agree that you don't need to choose this place. Yeah, and there are actually n possibilities of choosing this position. Yeah, I agree that you don't need to choose that place, but what is in that place you need to specify. You need to specify what is in that position. Yeah, and there are 6 possibilities for that position, because we already said there can only one can be exactly 3 times. One cannot be in that position.
So basically, it's not for the choosing; it's for what number can come.
Yes.
Okay.
Yes.
Thank you, sir.
Yeah.
Sir, one doubt
That was a good point actually. Yeah.
Sir, why it can't be chosen, sir? Can you explain why its position is fixed?
So let me ask you a simple question. Okay, you toss the head 10 times. Sorry, toss the coin 10 times. Yeah. How many possibilities how many ways can you see 3 heads? Is it 10C3 into 10C7?
No, sir.
It is 10C3. Right?
Yeah. Yeah.
But then you have to also choose the position for ones, no? Or sorry, the tails, no? So this should be the answer.
Okay. Sir, but if it is inherent that the others will be tails.
Yeah, it is inherent. So if you have chosen the choices for 1, 2, and 3, it's inherent that the rest of the things has to be the other 3.
Okay.
So that's why we didn't have to multiply here by I don't know, n also there.
Sir, I have a doubt.
Yeah.
So here we are picking up like 3, like 1 should be 3 times and 2 should be 4 times and 3 should be 2 times. So suppose after first toss you get a 2. You get a 2 after the first toss you get a 2. So there is a 9. So the 2 is also having the equal probability, right? We are not considering that ordered selection. So the 2 is also getting the probabilities instead of 7C4 should be 9.
Don't confuse yourself. Okay, it's extremely important in okay. So there is a sample space. So these are all the possibilities that you can get. You agree?
Yes.
There are 6 raised to 10 possibilities. The first dice could be any of the 6. Second dice could be any of the 6. Yeah. Among the set, how many elements are there which satisfies this condition? Yeah. So 1 should be there 3 times. So among this 1 to 10, we need to find 3 places where you want to put 1. How many ways you can do it?
10C3. Yes.
But then you are remaining 7 places. Yeah. From the remaining 7 places, you want to find a place to put 2's. 4 places. How many ways are there?
7C4.
Yeah. Now you are only 3 places are remaining. From the 3 places, I want to put 3. Sorry. Yeah, 2 times. Yeah. From 3 places, I have to choose 2 places. Now 1 place is remaining. Yeah. Now I have to assign some number at that 1 place. And that number cannot be 1, cannot be 2, cannot be 3. Yeah, it can be only 4, 5, 6. So that's why I need to multiply by 3. There's actually no probability here. We are just counting the number of objects. Yeah, and the probability comes in the number of possible cases divided by total number of cases. That is the probability. Okay.
Okay.
Yeah. So okay. So actually, yeah. Today's lecture is almost over. Yeah, I can take 1 or 2 more questions. So I wanted to cover some base rules examples also. Maybe I will record the lecture and put it up later, or ask the TS to cover it as part of the Q&A session. Yeah, please.
Yes, sir. I have one doubt. So here in the end, we only had 1 dice left, where we had 3 options for 4, 5, and 6, right? So what if we had more than 10 dice and we wanted
Let's change this number. Let's say this is instead of 4, this was 2.
Yeah. So in the end,
So
we would
let's
have
write
3
down.
dice left.
Let's yeah. So let's say 10C3. Yeah. And then there was 7C2. Yeah. Then we have only 5C2. Yeah. And then there are 3 places remaining. Yeah.
Yeah. Yes.
So I should, strictly speaking, write 3C3. But that is 1 only. Yeah. And in those places, there 4, 5, or 6 should be sitting there. Yeah. 3 into 3 into 3 divided by 6 raised to 10. That fine?
So why did you put in 3C3 there? I didn't get that.
There are only 3 remaining places from which I have to choose 3 places. There's only one way of doing it, but this number is also equal to 1.
Yeah. Okay. Yeah, got it. Yeah.
Sorry. Okay, I guess some of you will have a lecture at 10:30. So yeah, let's stop right now. Okay. Yeah, I will evening. Yeah, I will have post one more video, or there's a Q&A session. Whatever problem I was going to cover is again there in the textbook. So please read the textbook. The reading material also you need to read. Okay. I mean, just listening to the lectures is not enough. And actually from next week, I'm planning to have more problem solving as part of the course. We'll come up with some ways so that you can solve a lot of problems in the next 2-3 weeks. Okay. So yeah, so thank you for now. Yeah, we'll see there'll be a problem session, a light quiz associated with this, as well as there will be a Q&A yeah, at the correct time. Okay, thank you.